Hello again. All right. So one of the things we did talk about was how to do an inversion, how to make an inverted index. And what we did cover was how to do it in memory. Um, when you do it in memory, it's really fast. It's really easy to code. But there is a downside to it. Um, what are the downsides? Well, the big one is there's a limited amount of RAM. So the random access memory that you have in the computer. Um, yeah, let's think about a good web crawl. Not as big as what Google has, but a good sized web crawl. You can get this from the Common Crawl. And it has in it easily 1 billion web pages. Okay, so let's think about this. So if you had 1 billion web pages, that happens to be, as you know, that's one on the giga. That's 10 to the 9. All right, so that's what billions are, is giga. So you have a giga of these things. All right, so now we've talked about, well, we're going to store, even something as simple as we're going to need to store things by document ID. All right, so 1 billion, and we've got 4-byte integers. And this is, this is to store just simply the doc ID once. But we've already talked about that in our index. We're going to store that doc ID for every term in that doc ID. I mean, so already, maybe what? There's at least 10, 20, who knows what is the average number of unique words in a document? Well, depends on what it is. If it's the Twitter, maybe not that many, but if we're writing regular web pages, there's actually, I'm sure there's more than 10, 20. You could say maybe there's up to 100 unique words in a document. Now, not only that, but we're going to store their counts as well. And all right, and don't forget that we have to store information about the words as well, the actual strings and things. But nevertheless, just if we wanted to store each of the document IDs once, so that's 4 bytes per document ID, that's giga, 10 to the 9th, that's just to store that once, that's 4 gigabytes. Okay, if it's on the order of 100 times that, getting close maybe for storing a really simple index, it's 400 gigabytes. Okay, and in fact, indexes that we really are going to want to have are actually going to have not just the document ID and the count of a word in that document, but they're also going to have positional information. They're going to record at what positions the terms occur so that you can do things in more sophisticated ranking algorithms, such as talking about, are these words close to each other in the document? So that you can construct phrase search. You can search for certain phrases in a document. We're not getting to that more complex notion of indexing, but the problem is quite simple. If you have only in-memory indexes, if you only are doing this in-memory inversion, as you approach larger collection sizes, you're going to run out of memory. What's our solution? We have to be able to use the hard drive, the file system. It could be a solid state drive, but we have to use the file system to actually store the index. And also, while we're doing the inversion, we have to use that extra storage to make this feasible and possible. All right. Now, there's one thing that's important to know about hard drives, and it's not as true for solid state drives, but it is true. Solid state drives are fast, but they're not anywhere near as fast as the memory in a computer. So let's talk about traditional memory and hard drive, the thing to understand is that there's just a huge number, and these numbers are a little bit out of date, but most likely their relative amounts are still good. And so you can look things up. That basically, if we want to access a part of our random access memory, this is the memory inside your computer, the RAM. You know, when you go buy your laptop and it tells you you've got 4 gigabytes, you've got 8 gigabytes. Some of you maybe even bought more, but this is the RAM. And this is where our programs are stored in the data. If you want to do RAM access, it's on the order of 100 nanoseconds to do that. All right. Now, if you want to do a hard disk, so this is hard disks. Again, we've got little spinning platters, literally mechanical devices with magnetic iron oxide type particles on them that have been magnetized to store zeros and ones spinning around at high speed. And we have a reader head on top of that. And as the disk spins underneath it, we can read zeros and ones. All right. So a hard disk seek. This is when the disk is spinning around and we're like, yeah, we want you to go to there and read that part of the file. All right. So in other words, this is basically the equivalent of a random access. So we are going to go to a specific part of a file. When we have to do a seek. Well, this just happens to only take 10 million nanoseconds. To put that in terms, that's 10 milliseconds. Okay. What's this difference here? So going to disk is 100,000 times slower. All right. So our in-memory inversion, the techniques that we use in it, where we've got this dictionary and we read in a document, oh, let's count those words, that's great, that's not a problem. But then we're like, oh, let's go scatter them all over add them to the correct postings. So we touch, oh, it's this term, and we grab that posting and we append to it. Oh, it's this term, and we grab that posting and we append to it. We're hopping all over the place. We can't do that on the hard drive and ever finish in time. Effectively, we're doing all these random accesses all the time for our algorithm. If we do that, it's going to be maybe 100,000 times slower. Maybe you can get it down to 10,000 times slower, but that's not a good functioning plan. So we need an algorithm actually that doesn't do that. One thing to note that's interesting fact-wise, my pens don't like this warm weather, and I need to probably get some new ones. Anyways, the thing is, that's random accessing. Hard drives don't like that. But reading sequentially, so this is when we open up a file, and basically we read it from beginning to end. So when we're reading sequentially, the great thing is you're basically the head that's reading the data off the platter is just sitting there for the most part, and the platter spins underneath it at high speed, and so those bits just fly off and just get sucked in. When we read sequentially, we are only 80 times slower than memory. And certainly if you're using solid state drive, that difference is even less. So that's a really fascinating thing. So, we can go only a certain amount slower if we go with the hard drive. That's not that bad versus gigantically different. All right, so we need some sort of algorithm that really deals in a very sequential fashion with this problem, ends up reading those files, sucks files in, sends files out, things like that, something like that. And, well, good thing is we do have a solution. Otherwise, we wouldn't be here today. The solution is to do what's called a sort-based inversion. And the key thing is it's going to end up using merge sort then. So merge sort is fabulous for working with hard drives. Certainly, probably was originally designed to deal with files on tapes. Anyway, so you're going to do sort-based inversion using merge sort. That's our ticket to freedom, or I don't know, success, whatever we want to call it. All right, so let's walk through this now. And so again, indexing. I am not happy with this pen. Try another one. Go with, that's a little better. Start with our documents. And then we go into our tokenizer. All right. And out of our tokenizer, remember that we're going to basically have something along the lines, when we have some, start with some document here. So let's say we have a document which is document 72, and it's something like the dog chased the cat. All right. Goes into our tokenizer, and out of our tokenizer, we get basically, it's broken into tokens. And so, we know that we're going to have some doc ID 72, and it's going to look up our tokens in our lexicon and go, all right, yeah, I've seen that string before. Here's its number back. Oh, I haven't seen that. And it's going to make it the next unique ID and send that back. So we're going to end up with that. We're going to know our doc ID, and we're going to have term IDs given to us, which are, could be like 1 for the, maybe it was the very first word ever seen in the lexicon, or the second one, depending upon how we're counting. And then dog was the 503rd word, and then for some reason we had seen chased earlier, and 1 and 1036. All right, so we get back a list of term IDs out of our tokenizer, and or the tokenization process, and we've got our document ID. That's all good. We've already covered that. So then we're going to go and we're going to count words or count terms, okay? And so now we're going to know that 1 occurs twice, and all these other words occur once in this document. Good. Now, what should we do with that? When we do in-memory inversion, once we have that data, again, we scatter it across the terms, and we say, yeah, doc 72, we go to term 1 and we say it occurred twice. Then for term 503, we go, doc 72 has 503 in it once, and we append all those. That's what our in-memory inversion does. But again, we're not going to really do that here because we don't want to just keep filling up our RAM until we run out of space. So instead, what we're going to do is we're going to send this data out to the hard drive. We're not going to retain any more than basically in memory. We're going to retain in memory a document at a time, plus whatever we need for that lexicon to be able to keep looking up strings and saying, yep, I've seen it before, it's ID 503, or I haven't seen it, now it's ID, 9 million, blah, 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 all right? So, got to keep our lexicon in memory. We're going to keep 1 document's worth in memory, but then we're going to spew that document out and then go fetch another document is the basic idea. We've got this constant stream of documents coming through, and the only thing we're really holding on to memory that's of substantial size is going to be the lexicon. All right. So what we do is we produce a stream out of here of tuples, which are term ID, doc ID, and then the count. And so for this little example, what we would be streaming out to the disk is a tuple 1, 72, and 2. The next tuple would be 503, 72, and 1. Next one would be 431, 72, and 1. And the final one would be 1036, 72, 1. So we're going to spit these tuples out. No problem there. Well, where are we going to put them on a hard drive, and how are we going to store them on the hard drive? Well, that is the question, and I am going to treat us to a new marker right now. All right, so what we do is we append the tuples. To a file. And when we write them out, as binary data. We're not writing them out as text, which is what you're very used to in everything that you've done probably with writing to files. It's very right, oh yeah, printf and stuff like that. No, you're actually you're going to open that file up and you're going to say, I'm going to open it up in binary mode, and then you're going to use the write commands, not the correct commands, but the ones to write to the file, but they would be correct as well. That means you can actually send out, oh, I have an integer, and when you send it out to the file, it's stored as 4 bytes. It's not stored as a series of characters, showing what that number is. For human reading purposes, it's written out as the 4 bytes. So we have a file then, and it's going to look something like this. Now, I will tell you that the file actually is one long linear sequence of bytes. We can portray it in this fashion and not feel bad about what we're doing, because we know that actually what we're going to do is we're going to read across, and when we get to the end, it's just like reading the page. We're going to go here, all right, and there and there. But truth is, inside the file, it's 1 integer, 2 integer, 3 integer, 4, 5, 6, and it's just one long stream of bytes, So we would write in here in binary format 1, 72, and 2. So this was, the word the in document 72 occurs twice. And again, then we would write our 503, 72, and 1, our 431, 72, and 1, etc. All right. And again, a reminder that then these things are all stored as 4-byte integers. Okay. And it's just those documents come in, they get tokenized, we count them, we stream out this, and we just keep appending to this file. Our memory requirements are as minimal as we can with our lexicon. All right. Now, this file here, so this ends up being, happens as it's pretty clear, this thing is sorted by doc ID. I only showed it starting here at 72 as the example. It started at document 0 or document 1 and was written out. Then document 2 was written out, and document 3. So it's ordered by doc ID. What we want is to get this file to be sorted by term ID, then by doc ID. And so our term ID is the notion of a primary key for our sort, and the doc ID is our secondary key for the sort. And so our goal is to sort these rows of the file, these tuples, such that the term ID becomes the primary key. And so we end up with all the term ones. And then for all those term ones, then things are ordered by doc ID. And then you will see we'll basically be only one small step away from, we can take a file like that and just read through it because it's inverted. It's now by term ID, and it's in the order of the doc IDs with their counts. And then we could write that, we could just read that in, stream it into memory, decide how to write it out in what format to the hard drive for our inverted index, and we're done. So our goal turns into how to sort this file. This is where our merge sort comes into play. All right, so we've got a file like that, and basically we reminder back to your basics of algorithms and data structures. Almost guaranteed no one in here actually did do file-based merge sort, if you even did merge sort at all, although it's really cool. Well, our first step is we're going to take this file, all right, and you're going to break it into chunks. And so this is all of our tuples here sort of represented. And what you're going to do is you're going to read in one of these chunks. You read it into RAM, and then you're going to sort it, and then you can just write it back in the same location. Okay, so read the chunk, as large of a chunk as you can comfortably fit in memory and still do sort on it. And in memory, you're going to use something that, one of your quick sort or other sorts of faster sorting mechanisms. And sure, merge sort in memory is also fast, so maybe you're merge sorting in memory, but you're going to read this chunk out, sort it, and write it back out again. All right. And in fact, why don't I draw this in sort of in quarters to make it look good. 1/4, 2, there we go. All right, so you read in this chunk. Now, of course, for a big problem that we would need to do this, we'd have many more than just 4 pieces. Anyways, so nevertheless, get this, and then that gives us, that file is completely in sorted order. And so let me write this again. We've got it in sorted order. It's not the whole file, but each chunk is sorted how we wanted it to. Great. So now all we need to do is merge these 2 chunks into a new one that's all sorted. And again, remember the merge algorithm where, I'm going to stream in, and again, we can easily read from this point in a file and this point of a file when it's a binary file, and we can seek to those 2 locations, and then we can start reading sequentially through the file. And as we're reading it, we're saying, oh well, which one of these tuples goes first? And then we write it out there. And then we have the next tuples to compare. And what about these? And we just write them out in order. That's the beauty of the merge operation here, is that it uses almost no memory at all. We just stream things into memory. We're doing comparisons at the tuple level. We're only really storing in memory, two tuples at a time. By the way, the other nice thing about this is it is actually parallelizable. And so especially if we have put our file in a file system that is actually, this file could be on a RAID device that's spanning multiple hard drives, so that we can actually read many parts of it simultaneously. That means, and if we've got multi-processor cores, which I'm sure we do today, you can actually do the merge in parallel, and you can write back out. And so you write out these chunks, and of course, then the next thing is you go and you merge these, and then you have one entire sorted file. Once you have the entire, again, you're going to have more than 4 chunks usually to start with. Nevertheless, once it's all merged, now we can read through it in order, and we can write out our inverted index to our file system. So this brings us to the wonderful point of, well, how should we store an inverted index on our file system? Now, this is the idea of storing an inverted index on a file system when you plan to never bring the whole thing back into memory. Okay, when you plan to go and it's time to get a postings for a term, you go to the hard drive and you fetch that postings, you read that postings into memory, and you use that for your ranking algorithm. You never read the whole inverted index into memory. The inverted index is in a file structure that is indexed so that you can quickly fetch the postings from the hard drive and only the postings that you need to do your ranking. You, in homework 2, you're going to build your inverted index, and your goal is just to save it somehow onto the hard drive, because later when you want to use it, you'll just read the whole thing back into memory, and then it's in memory, and then you'll do your retrieval. We're not going to bother with the notion. If you wanted to attempt this, you're welcome to, but don't attempt it and go, I couldn't get it done in time. Okay? Because homework 2 doesn't require you to do this. All you have to do is do the in-memory inversion and save it somehow to the hard drive so that you don't have to do the inversion again the next time. You just read that file in, put it in your data structure in memory, and you're ready to run your queries then. So what does a file format look like for a static inverted index? And I say static because we're talking about an inverted index where we're not adding new documents to it or deleting documents. So we're going to have a system that's basically like this. We're going to have one file. It's a 2-file approach, but we have one file that stores postings sequentially. One after another, after another, after another. All right. So it would look something along like the following. So envision you've got, it looks like a gigantic array. Okay. And we've talked about our postings going document, then count, document ID, then count, and so forth and so on. So again, we've got some document ID here, and we have some count. And then again, we have our document ID and our count. And this continues on all the way down through here. Now, we could have, for example, a document that, let's say, is composed. It only has 4 unique, I'm sorry, we have a term, excuse me, these are postings. We have a term that's only present in 4 documents. So if it's present in 4 documents, this is the first one, the second one, the third one, the fourth one. So go ahead and I'll just say that this here is term 0's postings. So it's in 1, 2, 3, 4 documents, and here are the counts for those. I'm not going to bother to make up numbers. All right, so that would be term 0. And let's just go ahead and say the next term actually was only found in 1 document. And so there's only this. So term 1 and so forth, and term 2, etc., all the way through. So we're just basically, we're going to put a postings for one of the terms, then the next and the next, which is super simple to make based upon our sorted file, because our sorted file goes by term ID and it's sorted already by doc ID. So all we have to do is read that thing and write out the term IDs. We don't even have to write out, sorry, you don't have to write out the term IDs. We just have to write out the doc IDs and counts. But you're like, well, wait a minute, how can I tell where one term starts and one term ends? This is where we have another file. So this is a 2-file system. So another file that we write at the same time that we make this one, it stores byte offsets into the postings file. So the idea here is we're going to have some term, and we're going to have some offset, how many bytes into that file that we need to go. And in fact, so this file is just a stream of integers. It's one integer after another integer. Boom, 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 boom. So term 0, all right, starts at, we'll just, even though we wouldn't need to put it, say that it starts at 0, we will, just to make it easy to understand. And then term 1 starts at offset 32. So term 0 starts here, but this is 4 bytes, and so this is 4 bytes in, takes you to here. There's 8 of these, so 32 bytes gets you to here. So that's where term 1 starts. And then term 2 starts at an offset of 40 bytes, which is just right there. Now you're like, well, how? So, okay, so I could use this file to find out where to go in this file to find the postings, but how far should I read? Don't I need to mark the end of it? Well, the nice thing is you can easily see that this is the start here, and this is the end. And so very nicely here, term 1, we can see we just subtract. All you have to do is look ahead to the next integer and go, yeah, that's a difference of 8 bytes. I know I've stored them as integers, so all I have to do is divide by, basically it's divided by 8. And thus I will know how many documents that term was in. All right, and then you can figure everything out. So that's pretty easy. You're like, well, how do I use this when I have a term? Well, the great thing again is we've put them in order. We know that each of these is 4 bytes. So it's really simple. Oh, term 2, what's its offset at? Well, 2 times 4 is 8. And so you know you're 8 bytes in offset to read here to know that this one starts 40 bytes into this file. So that's the way it works. I mean, this is just literally an array. This is just an array. When we've saved them in 2 separate files, and then we can index into them as necessary. So when it comes time to actually fetch a postings for a term ID, we go to this file and we do one seek into it to find out where that is, and we read the next entry to find out how long it is. Then we seek into this file and we read down the length that we've calculated, and we pull that into RAM, and we've got our postings for that term. So we reduce down to, for each term that we need postings for, 2 seeks. A seek here and a seek there. And then we read a little bit sequentially, and we've got our postings. So it's not as fast as memory, but it is, on the scale of things, really fast compared to rereading that whole collection and trying to calculate stuff. So we're able to look up which documents are where a term is present and how many times does that term occur in those documents really quickly, even when it's on the hard drive. Okay, and again, for homework 2, you do not need to implement it this way. Okay, you could if you wanted to, but again, there's no need for you to. And it's just easier the other way. Do what is easiest, okay? So let's talk about some quick variations. Since that's just the basics and the conceptual notion, one quick improvement that you could make is that you could do the in-memory inversion until, use up, a certain percentage of RAM. Maybe use up half the RAM or something. You want to leave some leeway for other stuff. Use up half the RAM. And then write out in sorted order. And so you would basically be writing out these sorted chunks. And if you kept track of where those chunks were as you wrote them out, then you would be prepared to be doing your merge immediately. So you could be doing, keep merging all these chunks until you were done. You wouldn't have to first break that file up basically into chunks and merge the chunks, you would write them out already sorted. And so that is a way to save some time and effort. Another thing that's very interesting is that CPUs, as we've talked about, are so fast, and hard drives are so slow that we can store each posting, or postings, I guess, in a compressed format so this saves space, and thus can read into RAM faster because we won't have as much to read. It's compressed. Compressed a little postings, and again, our postings actually could be really long, could be a big collection, but it's compressed. We don't have to read as much in. We could probably easily compress it by half, so we could cut in the amount of time that it takes to read it off disk in perhaps about half. But then wait a minute, it's compressed. But CPUs are so fast, and then use the CPU to uncompress on the fly as we do our algorithm. And so this is a widely used technique that basically it's like, yeah, if this thing is so slow, well, but if I can use something else that's super powerful and fast to compensate for that, that's actually a good deal. So even though you make the CPU do more work, it doing more work is not much actual real time compared to saving time getting things off of the hard drive. So compression is a huge win when we deal with our inverted indices. So they aren't actually stored, as I said, where, we have this simple format and it's 4 in bytes. We will actually, they could still be 4 in bytes and stuff, but they're unlikely to be. They're actually a compression scheme, and we can get them into memory and uncompress them on the fly very rapidly, depending upon the compression scheme that we use. And the nice thing is there's compression schemes that take advantage of the nature of the fact that the document IDs, for example, are in increasing order, and then all sorts of things. And most of the word counts are small. A book that talks really nicely about it is this book, Managing Gigabytes. Admittedly, we're way beyond managing gigabytes now, but the compression schemes and stuff are really well explained in there. It's an excellent textbook. All right, so that gives you a sense of when we can't do our inversion in RAM, how do we do it on the hard drive?